The signals are likely to be strongest from black hole coalescences, two small black holes, rotating around each other and then coalescing. I think we're just not clear how many of these there really are in the universe. But in fact, there are statistics on neutron-star coalescing systems is much better. I think we've got a pretty good idea of how many coalescences there are likely to be. And with the next generation of detectors, that's the advanced versions of both LIGO and Virgo, we should be guaranteed to detect these. So I think these will be the first sources, coalescences of compact objects that are likely to be detected. Well, it was very exciting at the beginning, in the late 1960s, early 1970s, when Joseph Weber first began to make his claimed detections. And so I was involved in Glasgow in building up some aluminium bar detectors there. And of course we didn't see any gravitational waves, and in fact nobody around the world saw any gravitational waves. But by that time the challenge of the technology had really got to me, trying to measure very, very small distances of very small displacements, and over short time scales. And really it's been that technological challenge all along that has kept me going, because we kept making improvements. We moved from bar detectors to interferometers, learned new techniques, and just generally the field has always been very exciting for the experimental physicist. And really that is what has kept us all going, in fact. And very recently, with the present generation of interferometers beginning to operate and beginning to produce results that are astrophysically significant now, I mean, things are getting even more exciting. And so we're very keen indeed to make the improvements needed to both LIGO and Virgo, to allow these detectors to be a factor of 10 or so more sensitive, because we're pretty certain then that we're going to have guaranteed detections of gravitational wave signals from neutron-star coalescences.
And I was a graduate student in the early 80s in the University of Texas at Austin, with John Wheeler was at that time, and what motivated us to go into relativity, it's a little different to what got us excited recently. We wanted to, prove theorems, pencil and paper type of work, but at that time Kip Thorne was going around the country telling people, and in particular young students, that there's a new field that was going to be opened soon. And these measurements of distance to us sounded impossible. I mean, but some of us got convinced that was a huge opportunity, and we kind of move in that direction, and that's what has motivated us in the field of numerical relativity, which is what I do, to focus our work mostly to help in the detection of gravitational waves that these interferometers will be hopefully doing in the next, within the next 5 or 10 years. For some cases, you just need either the back of the envelope, the analytic, a little more improved than just back of the envelope, the analytic. But if you want to know the details of the system, in particular in the case of the binary system, when they're in the process of merging, there is no other way to do it by solving Einstein equations in full generality. And in that case, you had to do it numerically. There is no hope for any analytic solution. Now, that is still, it's a challenge, because even that we know how to solve what is called the two-body problem in general relativity, these simulations are still very expensive. It takes, for just one simulation, sometimes takes a couple of weeks in a supercomputer. So it will be impossible to cover all the cases that will allow us to specifically pick the case that nature is giving us in this detection. So to answer the question that show, yes, you can do it with some approximations, but ultimately I think you need to solve Einstein equations numerically. I mean, for instance, there were some phase transitions in the early universe that left behind this relic of gravitational waves that An example in the electromagnetic case is cosmic microwave background radiation that we have learned aspects of the universe very early on. There would be a similar backgrounds produced by phenomena taking place very early on in the universe that would allow us to investigate those epochs in a different way from what we have learned in the electromagnetic part. There is also exotic objects like cosmic strings that, as they evolve and interact, they also produce gravitational radiation. Those objects, we believe that if they exist, happen very early on in the history of the universe. That is another example that would allow us to know more about our universe very, very early on.
I think one thing we can also do, which is very important, is we can measure the expansion of the universe with both the ground-based detectors and with the spaceborne detector LISA, which is planned, to fly around about 2018 or so. And this is done, this is possible because of the fact that neutron star binaries act as standard sirens, or like standard candles, and so it's possible to tell absolutely the distance to them. And this means that we actually are able to at least check the electromagnetic measurements of how the universe is expanding. And this may be very important in our understanding of what dark energy is at some future time.
I think either way will be very interesting. I mean, why all our predictions are wrong, okay? Actually, even if you get a detection, if there is some mismatch with the predictions that we're making from using Einstein's theory of relativity, that will be also very interesting. There is a large body of research in our field that is aimed in that direction to see if there are other alternatives to Einstein's theory. But so far the indications that we have by that indirect measurements is that we have a strong evidence that Einstein was right. And, but there is still room there, and I think we should be open.
Λοιπόν, θα δώσουμε τώρα το λόγο στον κύριο Στεργιούλα και στον κύριο Περιβολαρόπουλο να μας πούνε τα σχόλιά τους πάνω σε αυτό. Μετά θα παίξουμε και ένα βίντεο, κύριε Περιβολαρόπουλο, για την κοσμολογία, οπότε εκεί θα μας πείτε και την δουλειά που κάνετε. Αλλά θέλω να πω κάτι εγώ τώρα τους τηλεθεατές, ότι όταν κάνουμε τέτοιες εκπομπές έχουμε ένα βασικό πρόβλημα. Σε ποιον απευθυνόμαστε. Διότι στο τέλος βγαίνουμε χαμένοι. Οι μεν που θέλουν να το πάμε πιο βαθιά και πιο επιστημονικά θα πούν ότι το πήγατε ηχά. Άμα το πάμε πιο βαθιά και πιο επιστημονικά θα βγουν οι δε και θα πούν δεν καταλάβαμε τίποτα. Λοιπόν, προσπαθούμε λοιπόν να είμαστε στο μέσο όρο, αν τα καταφέρουμε. Τώρα, αν το καταφέρουμε ή όχι, θα τα δούμε αύριο στο πόρταλ εδώ της εκπομπής με τα σχόλια που θα δεχθούμε και να ακούσουμε τον κύριο Στεργιούλα και τον κύριο Κόκκοτα και τον κύριο... από ένα σχόλιο δηλαδή στα τι είπαν οι συνάδελφοί τους για να περάσουμε μετά από ένα διάλειμμα που θα κάνουμε στην κοσμολογία.